Namaste, I'm Rohan Ramachandran, undergraduate fourth year in aerospace engineering at Amrita VisvaVidyaPeetham. My co-author is Professor Narayanan Komarath at the Taksha Institute in Hampton, Virginia, USA. Our paper is on the loads encountered during aerial rendezvous between two vehicles used to assemble a high-altitude long-endurance aircraft. The problem is how to map weather continuously and with high resolution over the whole planet in order to support climate prediction. As you see here, a very large part of the planet is open ocean, especially the Pacific Ocean and the South Indian Ocean. We are developing vehicles that can stay up indefinitely and map these areas as well as anywhere else above Earth. This slide shows an overview of our paper. Solar-powered high-altitude aircraft can be developed with indefinite endurance through day and night above controlled airspace if they can be assembled in flight. We are studying the forces and moments that may occur during such rendezvous. Upper bound loads are well within control authority. The actual loads seen in flight simulation are well under the upper bound limits. Now, HALE aircraft requires large aspect ratio and very low wing loading. In fact, if the wing loading is less than 1.25 Newton per meter squared and the profile drag coefficient is less than 0.025, we can design solar-powered vehicles that can stay above 18.3 kilometer or controlled airspace through 12-hour night before climbing back to over 30.5 kilometer in the daytime. Such a HALE vehicle is too long in span to take off from runway, as you can see in this figure. In our architecture, the large ultralight flying leaf vehicles are assembled from smaller flying leaflets. 6 out of the 9 FLTs return back to base once the flying leaflet is assembled. Our interest is in the aerodynamic loads that are encountered during the rendezvous. The baseline FLT is shown in this figure. Main point to note is the sheet edge frame where the rendezvous is to occur. For this simulation, we were not able to use multiplayer simulation in Explain 12. So the first aircraft is a so-called AI craft which has a mind of its own. Our method is to combine basic theoretical aerodynamics with a physics-based flight simulation called Explain 12. The flowchart of Explain 12 is shown here and in the paper. Now, this is a short video demonstrating the rendezvous. So here, the first FLT takes off from runway 04 in Agatti. The setting is 9 a.m. in the morning. As it climbs, it turns west heading 270. And then it climbs up to the required altitude. Simultaneously, the second FLT takes off from the same runway and tries to meet up with the first FLT for performing the rendezvous. And as you can see, the other aircraft, the furthermost aircraft is the AI craft. And both these FLTs are coordinating for performing the rendezvous. And here is the rendezvous where both the wingtips join. And this is what happens when two FLTs join after performing the rendezvous. Main point to notice is the sheet edge frame, which you can see on the top. And this is all part of a project, Project Coverity. Now, as you can see, this particular figure has a very long span. So this justifies why you can't take off from conventional runways. In future, we expect to have such swarms over much of the planet doing meteorology. Now, this slide shows conceptually what happens when two FLT come close together. We use concepts from vortex flow aerodynamics and Plantin's lifting line theory. Each lifting surface has a vortex system consisting of bound circulation around the wing, tip vortex at each end, and span-wise vortex sheet trailing behind as the bound circulation changes. I'm not showing the vortex sheet. Focusing attention on the edges of the two upper sheets and their tip vortices, we see that each tip vortex will induce velocity outboard and thus increase angle of attack near the tip of the wing. Thus, outboard lift will increase, causing a rolling moment on each wing up and away from the other wing. The roll will tilt the lift vector, causing side slip away. However, lift-induced drag will increase at each wingtip, countering the side slip with yaw, bringing both the wingtips together. Assuming a maximum area of influence on each wing and the absolute maximum magnitude of each tip vortex, we used Biot-Savart law to calculate the upper bound of the lift increase. We then compared this with the actual lift changes seen in flight simulation and at different separation distances. So what is shown is actually a set of points starting at the closest separation and then at 3 seconds as the AI aircraft tends to move away. For low rates of acceleration shown, we can treat the problem as quasi-steady. So the loads are same whether approaching or moving away. We repeated the maneuver 5 times and have shown the loads. Some came out to be negative, as you can see in Rendezvous 1 and 4, but all were well under the projected maximum, which is under 5% of total lift. Now the question arises, what will happen as rendezvous occurs after the flying leaf is partially assembled? This slide checks that. We have seen the worst case is what we just showed, the first rendezvous. And as the loads are, after that, the loads are smaller and smaller percentage. And by the last one, you can see the upper bound is hardly 1% of the total lift. Now this slide shows our continuing work. We hope to have the full multiplayer function working soon and then study several load histories at detail at different configurations and altitudes. Now these are my conclusions. Initial foray into most risky assumption, ability to assemble long span HALE in flight from smaller vehicles. Rendezvous between two FLTs is done in initial physics-based flight simulation. Both vehicles experienced increased lift and drag at rendezvous edge, causing outward rolling moment and inward yawing moment with small net load. Post-rendezvous, overall lift increases and induced drag decreases. Theoretical upper bound lift perturbation is under 4% for 1-to-1 FLT rendezvous. As flying leaves are assembled, perturbation falls under 1% of the last rendezvous. Simulation with randomly moving AI aircraft in Explain 12 shows scattered load within predicted bounds. Therefore, the objective of this paper is met. Further refinement is left to a full simulation of all cases and actual flight testing. Thank you.